At dawn, the beach looks almost impossible. The water does not rise first, it leaves. A smooth sheet of sea rushes backward across the sand, faster than a normal tide could ever move. Shallow pools drain into long silver lines. Rocks that were underwater a minute ago glisten in the open air. A small boat tilts on wet sand where waves should still be lifting it. The shoreline keeps moving away, farther and farther, as if the ocean has been pulled by an invisible hand. For a few seconds, the scene can look strangely calm. There is no wall of water at the beach yet. There is only exposed seabed, stranded marine life, and a sudden silence where surf should be. But far out on the horizon, the line of the sea has changed. It is darker, it is thicker, it is beginning to rise. That empty beach is not safe. It may be the warning. When the ocean suddenly pulls back before a tsunami, the water is not making room in any simple sense. It is revealing the shape of a wave so large that a normal human sense of waves is almost useless. A tsunami is not just a tall breaker rolling across the surface, it is the movement of an enormous volume of water, sometimes set in motion by the seafloor itself. If the first part of that wave to reach a coast is a trough, the sea level can fall dramatically. Water drains away from the shore because the lower part of the wave arrives before the higher part, then the crest follows, and the sea comes back with a force that is nothing like a returning tide. To understand why the ocean can pull back, begin below the surface, far from the exposed sand. Imagine a section of seafloor locked under pressure for years, decades, or even centuries. Two slabs of Earth's crust are pressed together along a fault. They do not slide smoothly. They stick, stress builds, rock bends. The ocean above seems ordinary because the movement is hidden deep below. Then the fault slips. A huge patch of seafloor can jump upward, drop downward, or move in a way that suddenly displaces the water above it. The ocean is heavy, but it is also connected. When the seabed shifts, it pushes or pulls on the entire water column above that patch, from the seafloor toward the surface. The disturbance spreads outward in long waves. These waves may cross an ocean basin with astonishing speed, but in deep water, they may barely look dangerous at the surface. A ship far offshore might rise and fall gently without seeing a dramatic wall. The energy is not concentrated in a curling top like a normal wind wave. It is spread through a deep, long, moving body of water. The wavelength can be so long that the crest and trough are separated by many miles. That is why the first sign at the coast may not look like the wave people imagine. The first sign can be the wrong thing, the ocean going away. A normal beach wave is made mostly by wind pushing on the surface. It breaks, foams, and collapses in a familiar line. A tsunami behaves differently because the whole water column has been disturbed. It is more like the ocean being rearranged. The surface is only the visible skin of a much deeper motion. The sequence depends on which part of the tsunami reaches the coast first. If the crest arrives first, the water may rise rapidly without a dramatic retreat. If the trough arrives first, the shoreline may drain. Both can be dangerous. The retreat is not a promise that every tsunami will do the same thing. It is one possible natural warning sign, and when it happens, it can be deadly because it tempts people to look. The exposed seabed is visually powerful because it feels like a rare invitation. A person might see fish on wet sand, boats leaning over, reefs exposed, and a horizon that seems far away, but the retreat itself is a moving part of the wave. The water is not gone. It is being drawn into the larger motion of the tsunami. The danger is already in progress. Now watch what happens as the wave approaches shallow water. In deep ocean, a tsunami can travel fast because the water column is deep. The wave is long and low, so its energy spreads across distance. But as it enters shallower water near a coast, the lower part of the wave begins to feel the seafloor. The wave slows. The back of the wave is still pushing forward. The energy has less depth to occupy. Water piles upward and inward. The wave grows. This is called shoaling, and it is one reason a tsunami that looked almost invisible offshore can become destructive near land. The same energy that was spread across deep waters compressed into a smaller vertical space. The wave does not have to look like a perfect curling wall to be deadly. It may arrive as a fast-rising flood, a violent surge, a steep bore, or a series of rushing waves. The beach that drained earlier now becomes a channel. Water that pulled away returns across the exposed seabed, but it does not return gently. It advances with the momentum of a long ocean wave, carrying foam, sand, broken objects, and debris. A boat that was tilted on wet sand may be lifted, spun, and driven inland. Water can surge through streets, around buildings, into harbors, and up rivers. In some places, the first wave may not be the largest. The sea can return again and again with minutes or more between waves. That is why going back too soon is dangerous. A tsunami is not a single splash, it is a train of waves. The pullback before a tsunami can be understood by picturing a wave as having two broad parts: a crest, where water level is higher than normal, and a trough, where water level is lower than normal. If the trough reaches the shore first, local sea level drops. Water drains toward the approaching low part of the wave. Because the tsunami wavelength is so long, that drop can expose a large area of seabed. The beach does not simply lose a few feet of surf. The entire shoreline can shift. The amount of retreat depends on the shape of the wave, the slope of the seabed, the shape of the coastline, and the direction of approach. A broad, gently sloping beach may expose much more seafloor than a steep rocky coast. A harbor, bay, or inlet may amplify water movement in unexpected ways. Underwater ridges and coastal geometry can focus or redirect energy. Two communities, only a short distance apart, can experience very different flooding. This is why tsunami behavior can be so deceptive. The ocean does not deliver the same visual warning everywhere. In one place, the sea may suddenly withdraw. In another, it may rise. In another, the water may surge sideways through a harbor before a clear wave front appears. A person watching only for a dramatic wall might miss the danger. A person watching only for retreat might also miss the danger. The safest rule is broader. If you are near the coast and feel a strong or long earthquake, or see the sea suddenly rise or fall, or hear an unusual ocean roar, move immediately to high ground or inland. Do not go to the exposed beach. Do not wait to see the wave. The empty beach is not a spectacle. It is a countdown. Under the water, the physics is still unfolding. When the trough reaches shore, water level near land may be pulled down. When the following crest arrives, water level rises. But because the sea is already drained away from the beach, the returning water can travel across a newly exposed surface. It gains a terrifying visual clarity. The horizon darkens, the sea edge thickens, and the first white lines of turbulence appear where deep-moving water meets shallow ground. The horizon may not look like a movie wave. May look like the ocean standing up. Sometimes it appears as a dark blue ridge, sometimes as a churning line, sometimes as a sudden elevation of the sea surface, wide and relentless. By the time the shape is obvious, the safe moment may already be gone. The correct response to a sudden ocean retreat is not filming, collecting fish, or walking farther out. It is leaving immediately. The reason the retreat can be so fast is that it is not a tide. A tide is driven by gravity from the moon and Sunday and changes over hours. A tsunami withdrawal can happen in minutes. The water can rush seaward with enough force to create strong currents, exposing sandbars, rocks, and harbor bottoms. The speed of the retreat itself is a warning. If the ocean moves like a time-lapse tide, nature is sending a signal that belongs to a very different scale of energy. That scale begins with displacement. When the seafloor moves suddenly, it does not push only a thin sheet of surface water, it moves a vertical mass. That is why tsunamis can carry energy across entire ocean basins. The ocean surface may rise over the uplifted seafloor and sink over the lowered region, creating alternating crests and troughs that spread outward. The exact first arrival at a coastline depends on the source motion and wave pattern. A downward initial displacement can send a trough first in some directions. An upward displacement can send a crest first in others. The coastline only sees the part of the pattern that reaches it. This is also why a tsunami can arrive long after the shaking stops. Near the source, the first waves may arrive within minutes. Across an ocean, travel time can be hours. Modern warning systems use seismic data, sea level gauges, deep ocean sensors, and modeling to estimate where waves may go. Those warnings matter, but natural signs also matter, because if you are close to the source, There may not be enough time to wait for an official message. The ground may be the warning before the sirens. Strong shaking makes it hard to stand. Or if shaking lasts a long time near the coast, the safest action is to move away from low coastal areas as soon as it is safe to do so. The ocean retreat is one possible sign, but the earthquake itself can be the first sign. The goal is not to predict every wave by eye. The goal is to recognize that the coast has become dangerous. A tsunami also changes when it meets the shape of land. A straight coast, a funnel-shaped bay, a narrow harbor, a river mouth, a reef, or a continental shelf can all change the way water piles up. In some places, the wave height increases dramatically because the water is squeezed sideways and upward. In others, strong currents may be the main hazard, tearing through harbors and channels. Even when the wave height is not spectacular, a tsunami is dangerous not only because of vertical height, but because of moving water volume. Moving water is heavy. A knee-deep fast current can knock a person down. A deeper surge can move vehicles, boats, building fragments, and trees. Debris becomes part of the flow. The first incoming water may look like a rough flood, but the outward flow after it can be just as dangerous, dragging debris and water back toward the sea. Then another wave can arrive on top of a changed landscape. That is another reason the pullback is so important to understand. The retreat before the first wave is only one version of withdrawal. Water can also pull back between tsunami waves. After a surge floods inland, the ocean may reverse and drain violently, carrying debris seaward. That withdrawal does not mean the event is over. It may be setting up the next incoming wave. The ocean can breathe in and out with destructive force for hours. And official all-clear messages exist because the danger lasts longer than the first visible impact. The most dangerous illusion is that seeing the water means understanding the wave. A tsunami does not show all of itself at once. The visible front is only one piece of a long sequence of crests, troughs, currents, reflections, and local amplification. In a bay, waves can reflect and slosh. In a harbor, currents can continue after the first major surge. Along a coast, the shape of the land can turn the same incoming wave into different hazards from one beach to the next. So the ocean pulling back is not the tsunami starting. It is the tsunami already arriving. The trough has reached the coast. The water level has dropped. The crest may be behind it. The system is in motion. That is why the exposed seabed should be read not as an empty space, but as a message written in moving water. The message is simple: leave. To make the picture clearer, shrink the ocean into a cross-section. On the left, the deep sea floor suddenly lifts. Above it, the water surface bulges upward. But gravity does not allow that bulge to stay in one place. Water begins to move outward. One side of the disturbance becomes a crest. Another part becomes a trough. The pattern spreads like a giant ring, but it is not a simple ripple in a pond. The scale is too large. The depth is too great. The energy is moving through the full water column. That is why the word waves can be misleading. People hear wave and imagine something they can watch time and outrun if it is far enough away. But a tsunami wave near shore is often less like a single object and more like a rising, rushing body of ocean. The front can be broken, muddy, and filled with debris. It may not curl neatly. It may not even look high at first. A waist, high surge moving with ocean. Scale force can still be deadly, and a larger surge can reshape a coastline in minutes. The water's direction can also change with terrifying speed. During the drawdown, everything moves seaward. Channels form across the exposed seabed. Boats pull against moorings. Harbor water can drain so quickly that floating objects settle onto mud or lean against docks. Then, when the crest arrives, the direction reverses. The same channels that drained water away become pathways for return. Any loose object can become a projectile. Any low road can become a river. The coast becomes a machine for focusing water. A bay can behave like a funnel. A harbor can trap energy and turn it into violent currents. A river mouth can carry the surge inland beyond the visible beach. A reef can break part of the energy but also create complicated flow around gaps and channels. Even the slope of the beach matters. A gentle slope can let water travel far inland. A steep coast may show less retreat but still experience powerful run-up. Run-up is the height the water reaches above normal sea level on land. Inundation is how far the water travels inland. Neither is measured by looking at the first thin line of water at the beach. A tsunami can climb, surge, reflect, and keep forcing water into low areas. The wave's height at the shoreline is only one part of the hazard. The speed, duration, debris, and number of waves all matter. This is why the safest response is not based on curiosity. Curiosity says, the ocean has pulled back. Go see what is exposed. Science says, the trough may be here, the crest may be next. Curiosity says, the first wave passed, go back and check. Science says, a later wave may be larger. Curiosity says, the water is only a few feet deep. Science says, moving water carries momentum, debris, and the weight of the ocean behind it. The most haunting part of a tsunami retreat is that it can make danger look like discovery. A reef appears, a harbor bottom opens, fish flap where water used to be. Sandbars connect to places normally cut off by sea. The human eye reads novelty before it reads risk. That delay is exactly what makes the warning so urgent. A tsunami does not care whether the beach looks peaceful. It is governed by energy, depth, and time. The same physics that pulls the sea away can also make the return arrive from more than one direction. Water can wrap around headlands, reflect off harbor walls, and collide with incoming flow. Streets can fill from the ocean side while canals, rivers, or drainage channels surge from behind. The coast may not flood like a bathtub. It may be attacked by moving water pathways. Even after the first incoming surge weakens, the outgoing water can be destructive. As water drains back toward the sea, it drags debris with it. Cars, timber, boats, roof pieces, docks, and sediment can move together. The outgoing flow can scour ground, undermine structures, and pull objects into channels. Then the next incoming wave may ride over a landscape already broken and rearranged. That is why official instructions often emphasize waiting. The ocean may look calmer between waves, but the wave train can still be active offshore. Instruments and authorities may still be tracking dangerous sea level changes. People who return during the pause may be caught by a later surge. The absence of water is not proof of safety. The absence of noise is not proof of safety. The end of one visible wave is not the end of the event. There is another misconception hidden in the phrase, the ocean pulls back before a tsunami. It sounds as if the retreat is a required opening act. It is not. Some tsunamis arrive as a rise. Some arrive with little visible drawdown. Some are noticed first as strange currents in harbors. Some are local and fast. Some are distant and announced before the coast changes. The same tsunami can produce retreat in one location and a rise in another. Depending on wave phase and coastal shape, the rule is not wait for the ocean to disappear. The rule is treat unusual sea level change as danger, and treat strong coastal shaking as danger, even before the ocean changes. A good warning message is simple because the situation is not a classroom test. If the ground shakes strongly near the coast, go to high ground. If the water suddenly recedes or rises, go to high ground if officials order evacuation. Go if you are already in a safe place. Stay there until the all clear. The science matters because it makes those rules feel real. The retreat is not a magic omen. It is not the sea breathing in anger. It is the visible trough of a long wave interacting with shallow coastal water. The horror comes from the fact that the mechanism is natural, physical, and indifferent. The ocean is not choosing to warn anyone. It is simply exposing part of its motion before the rest arrives. Now return to the seafloor one more time. The rupture does not have to lift every part evenly. Some sections rise, others sink, and some slide sideways. The water above responds to that shape. The first waves that radiate outward carry the imprint of the seafloor movement. In some directions, a crest leads. In others, a trough may lead. By the time the wave reaches a distant coast, it may also have been shaped by deep ocean ridges, island chains, and continental shelves. The coastline receives a message that has been rewritten many times by the ocean basin. That is why tsunami forecasting is complex. It is not enough to know that an earthquake occurred. Scientists need the earthquake's location, magnitude, depth, fault movement, and how the water actually responds. Sea-level instruments help confirm whether a tsunami was generated. Models estimate arrival times and possible impacts. But the models are tools, not permission to ignore natural signs when you are near the source. Close to the source, the first warning can be physical. The ground shakes, the sea changes, the roar begins. In those minutes, the safest decision is not to solve the entire event. It is to move. For a documentary camera, the retreat is cinematic because it reverses expectation. The ocean is supposed to attack by coming in here. The first frightening image is withdrawal. The emptiness is the hook. The silence is the tension. The exposed beach is the trap. Then the horizon rises and the true scale of the wave becomes visible. But for real life, that cinematic sequence is exactly what should not be watched from the shore. The best view of a tsunami is from a safe elevation, far from the inundation zone. After evacuation has already happened, the best footage is never worth a life. The ocean's pullback is powerful precisely because it gives a short visual clue before the greater force arrives. The correct response is to use that clue, not study it from the danger zone. There are also places where the retreat may be hidden. At night, people may not see the exposed seabed in a storm. Unusual water movement may be harder to recognize. In steep coastal areas, the water may not withdraw far across a broad beach. In harbors, the first sign may be violent currents rather than a clear, empty shoreline. In river mouths, the water may surge upstream with little warning to someone looking only at the open beach. So the lesson expands beyond one image. A tsunami warning sign can be a sudden fall in sea level. It can also be a sudden rise. It can be strong shaking. It can be a long earthquake. It can be a strange roar. It can be an official alert. The retreat is dramatic, but it is not the only door into the hazard. Still, when it appears, it is one of the most unforgettable. The beach transforms into a landscape that should not exist. The bottom of the sea lies open. The familiar boundary between land and water is erased, and far beyond the exposed ground, the ocean is already reorganizing itself for return. That return is not just height, it is duration. A wind wave breaks and passes in seconds. A tsunami surge can keep coming. Water pushes, piles, and keeps pushing. The flow can last long enough to fill spaces that a normal wave would only splash. It can turn streets into channels and buildings into obstacles that split the current. It can carry sediment inland and then pull debris back out. The event is not one dramatic impact. It is a long argument between moving ocean and fixed land. The land often loses. This is why waterline marks after tsunamis can be so revealing. They show where the surge reached, how high debris was carried, and how far the water traveled beyond the normal shore. They also show that the most dangerous water may not have looked like a perfect wave at all. It may have looked like a fast flood with ocean behind it. The empty beach at the beginning and the waterline mark at the end are two halves of the same story. First, the trough lowers the sea later. The crest and following waves leave their height written on land. Between those images lies the entire mechanism. Seafloor displacement, long wave propagation, shallow water slowing, energy compression, coastal amplification, repeated surges, and withdrawal. That mechanism is why a sudden pullback should never be treated as a mystery to investigate from the sand. It is a message arriving in the only language the ocean has. Movement, when the sea suddenly leaves. The question is not where it went. The question is what part of the wave is coming next. Imagine the dawn beach again. The surf line has retreated so far that the wet sand shines like a mirror. Boats lean at angles. Rocks appear where there should be waves. The air grows quiet not because danger is absent, but because the usual sound of surf has been pulled away. The horizon looks wrong. A dark ridge begins to lift across the line between sea and sky. The mechanism is invisible, but its signs are visible. A fault moved. A water column shifted. A long wave crossed deep water. The trough arrived first, the coast drained. Now the crest is approaching shallow water, slowing, growing, and pushing the ocean back toward land. There is no need to measure it. There is no need to wait until it looks cinematic. The correct moment to act is the strange moment, the impossible moment, the moment the ocean leaves. A responsible understanding of tsunami retreat must also leave room for the cases that do not look this way. Sometimes the first arrival is a sudden rise. Sometimes the first visible hazard is a surge in a harbor. Sometimes distant tsunamis are announced by official warnings before any natural sign is visible. Sometimes local conditions hide the warning until water is already moving dangerously. The ocean's behavior is not a script. Warning signs are clues, not guarantees. But when the sea pulls back suddenly and unnaturally, it is one of the clearest natural warnings the coast can give. That is why old accounts of tsunamis often describe people walking onto newly exposed sea floor, confused by the sudden retreat, only to be overtaken when the water returned. The tragedy is not only the wave, it is the false safety before it. The ocean appears to offer space, and that space becomes the path of return. Science turns that frightening image into a pattern. The trough lowers the water. Gravity and wave motion draw the sea away. The following crest brings it back. Shallow water compresses the energy upward. Coastal shape can amplify the surge. Multiple waves can follow. Strong currents can continue after the first impact. None of these pieces require myth or exaggeration. The physics is powerful enough. The warning is powerful because it is visual. Most hazards hide until they strike. This one can briefly reveal itself by removing the sea from where the sea should be. It exposes the bottom. It silences the surf. It changes the horizon. It turns a familiar beach into an impossible landscape. That impossible landscape is the last thing anyone should approach. If you are near a coast and the ocean suddenly retreats far beyond normal low tide, move to higher ground immediately. If official evacuation orders are issued, follow them. If you feel a strong or long earthquake near the coast, do not wait for the ocean to pull back. Go inland or uphill. Stay away until authorities say it is safe. The first wave may not be the largest, and the water may keep moving dangerously long after the first surge. The beach at dawn is empty now. The exposed sand shines, the boat is still tilted. The rocks still glisten. Far out, the dark ridge has grown taller, not as a single curling wall, but as a moving rise of ocean that fills the horizon with weight. The sea left because part of the wave arrived as a fall. It returns because the next part is a rise. And by the time the ocean comes back, the safest place is no longer anywhere near the shore,